Hello again. This is John Guttag, welcoming you back to another exciting segment in 600X. We ended the last segment looking at ways in which we can use the standard deviation of a normal distribution to construct confidence intervals and levels. We observed that normal distributions are quite common. If we were to plot the heights of all the students in 600, or for that matter the people in this large stadium, it would almost surely produce something close to a normal distribution. If one looks at the experimental errors in repeated trials of an experiment, they are typically normally distributed around zero. Well, I guess around zero if the experiment's well conducted. Otherwise, the mean is less obvious. If I plot the average temperatures for almost any place in the world, this happens to be in the United States, they will be close to normally distributed as well. It is important to remember, however, that not all distributions are normal. Consider rolling a single die. As we have talked about before, perhaps more than you enjoyed, each of the 6 outcomes is equally probable. If one were to roll a single die 1,000,000 times and create a histogram showing how often each number came up, each column would be almost the same height. If one were to plot the probability of each possible lottery number being chosen, it too would be a flat line, at 1 divided by the range of the lottery numbers. As we've discussed before, such distributions are called uniform. Uniform distributions occur frequently in games devised by humans, but only rarely in nature, and are not usually useful for modeling complex systems. They can be easily characterized by a single parameter, their range. In contrast to uniform distributions, exponential distributions occur quite commonly. They are often, for example, used to model inter-arrival times, the frequency with which autos enter a highway, or with web pages are requested. They're important because they're the only continuous distribution that has the memoryless property. What happens at one stage of the distribution is independent of what happens at other stages. Consider, for example, the concentration of a drug, and let's assume it's a legal drug, in the human body. We start with some finite number of molecules of the drug. The body's natural instinct is to try and eliminate foreign substances. So let's assume that at each time step, each molecule has a probability P of being cleared, that is to say, eliminated from the body. The system is memoryless in the sense that at each time step, the probability of a molecule being cleared is independent of what happened at previous times. Let's start at time t equals 0 and ask whether a molecule that was in the body at time t equals 0 still is. Well, of course it is. So the probability of that molecule still being there before any time has elapsed is 1. How about time t equals 1? Well, we know that the probability of the molecule being cleared is p, so the probability of it still being in the body has got to be 1 minus p. At t equals 2, the probability of that individual molecule still being there will be 1 minus p squared. And more generally, at time t equals k, it will be 1 minus p to the k. Notice, by the way, that this term could be written as 1 minus p to the 1, and this term could even be written as 1 minus p to the 0. So indeed we see this formula is correct at each time step. Now let's suppose that at time t equals 0, there are m0 molecules in the body to start with. In general, at time t, the number of molecules still in the body will be m sub 0 multiplied by what? By the probability that an individual molecule has survived. And that is the probability we just looked at. Let's look at some code that implements this to compute how many molecules are likely to be in the body at any point in time. The function clear has 3 arguments: n, the initial number of molecules, the probability of it being cleared at each step, of a molecule being cleared at each step, and the number of steps. We start by initialize num remaining to n, so at time t equals 0 there are n molecules. Then for each step we append to num remaining the value of the formula we just looked at. And then when we're done, we just plot it all. We can now look at the code in the code window. It looks like I've added labels for the x and y axes. That's a good thing. Now let's run it for 1,000 initial molecules, clearance probability of 0.01 and 500 steps. Well, we get this rather elegant exponential graph. This is an example of exponential decay. In practice, exponential decay is often talked about in terms of half-life. Half-life is the expected time required for the initial value to decay by 50%. For example, the half-life of a single radioactive atom is the time at which the probability of that atom having decayed is 0.5. What do you think will happen if I go back to the code and make the y-axis logarithmic? Well, that beautiful exponential decay has been replaced by a straight line. Are you surprised? Well, you shouldn't be. Because recall that the values on the y-axis were changing at an exponential rate. That's why it's exponential decay. And when we make the y-axis logarithmic, the labels on the y-axis are now also changing at an exponential rate, hence the straight line. This is one way to check, by the way, if distributions are exponential. Notice, by the way, that this code is not a Monte Carlo simulation. Even though I'm using a probability in this statement, there is no randomness in this code. Suppose I want to write a Monte Carlo simulation to test the same thing. Well, let's go look at that. ClearSim takes the same three arguments as clear, and again begins by initializing num remaining in the same way, and iterating through each step. For each step, it looks at each molecule, M, and either clears it or not, depending upon whether random.random returns a value less than or equal to the clear probability. Then when it's done, it plots it. The code down here first runs clear, and then ClearSim, so we'll now see in a single plot the results of both ways of computing the exponential decay. Notice that these two approaches give us almost identical curves. That's a good thing. I would have been worried if they hadn't. I also would have been worried, by the way, if they'd been identical, since for one, the simulation, there is some randomness, so I wouldn't expect it to exactly track the initial values, the theoretical values given by the blue curve. And in particular, as the numbers get smaller, as we've gone through more steps, I might expect more divergence because the law of large numbers would no longer be applicable. So to get a precise answer, it's better to calculate it from the probabilities. On the other hand, the simulation does have some value. Suppose, for example, I want to change it a little bit. In fact, let's do something a little bit strange. Let's assume that this drug is maybe not a drug, but say a virus or a bacteria, some kind of life form that can reproduce itself. And so let's modify this simulation to account for the fact that every 100 steps, each of the surviving molecules clones itself. We can do that quite easily. Let's put the code in here. If we're not at the first step, and the step we're at is evenly divisible by 100, we'll change the number of molecules left to be doubled. Num left plus equal num left. And then we'll go off and see what we get there. Well, here we see that the blue curve is, of course, unchanged, but the red curves, the simulation, is rather strange. It drops down till it reaches 100 steps, then it jumps up, drops down, but we see that it gets smaller and smaller, and we are getting ragged decay, but effectively it is still dropping exponentially. Kind of the fun thing you can do with simulations is try different kinds of experiments. Exponential growth is the inverse of exponential decay. It too is quite commonly seen in nature. Compound interest is an example of exponential growth, as is the growth of algae in a pond or a swimming pool. And the power of an atomic bomb is based upon the fact that the energy grows exponentially.